So hello, I'm going to just make a video about the derivation of the Poisson process. Just very shortly, what is the Poisson process, or what are we interested in? Let's imagine, say, a cinema, and within time a person arrives at the queue for he or she wants to wait for the movie, and still takes some time until the cinema opens. Then after some time, second person will arrive, third person will arrive, and so on. And the rate of people that arrive at the queue is independent of how many people are already waiting there. And in the Poisson process, we are interested for the probability that k people are waiting in the queue after a certain time t has already passed. And to derive this p here, let's first imagine a time interval, and the whole time interval, let's call it t. Or this time interval has the magnitude t, or last t time units. And let's make a cut in this interval and here call it s. So this sub time interval here is s, and so this is s, and the remainder is t minus s. And let's write this expression for p again. We are interested in pk of t. So now we can write this as the sum of products, because the amount of people that arrive in time interval s is independent of the probability of how many people will arrive in the remaining time. Or better said, in this, the probability of how many people arrive in t minus s does not depend on how many people have already arrived in time interval s. Therefore we can write it as p0. So 0 people have arrived, the probability that 0 people have arrived in s, times p that k people have arrived in the time interval t minus s, plus p1. Let's say if one person has already arrived in s, k minus one person must arrive in t minus s, and so on. And because of this, so here basically we sum up over all different combinations of what can stand here in the subscript. Therefore we can write this as a sum running from I equals 0 to k. I people arrive in time interval s times k minus I people arrive in the remaining time within s. And we can do this, as already said, because the arrival of new people is independent of how many people already have arrived. So now we will need this formal leader for the derivation, but now let's imagine h, and h is a time interval such that at most one person arrives, or one event takes place, more generally speaking. And therefore we can write that, and then lambda is the probability that is the probability of how many persons will arrive in unit time t equals 1. And therefore we can write an expression that p1 of h plus p0 of h, and h denotes a time interval such that at most one person arrives in this time interval, or one event takes place at most. So 0 or 1 persons can arrive, or 0 or 1 events can take place. And because with lambda we have defined lambda in unit time is the probability that so many people will arrive, or it's the probability, or let's say it's more like a rate how many people will arrive on average in front of the same, or how many events will take place on average. So therefore we can say that p1 of h equals lambda times h plus p0 of h, and the sum must be 1, because here we assume that h is so small that at most one person can arrive. Therefore p1 of h plus p0 of h must be 1. And here with h the number of people, the probability of the number of people that will arrive in unit time, or let's say the rate of how many people will arrive in unit time times this small h here. This denotes the probability that one person arrives in time interval h, and this is that no person arrives in the time interval h. Okay, good. And now we go back to the formula we already had, and with our time interval, which we divided, let's say, somewhere at time s. And now do this again, but so this is t, some time interval, and here we make the cut such that this is h in sorita, and this is t. Here the whole time interval must be h plus t. And because in h just one person can arrive, we can write pk of t, plus h equals bk minus 1. So k minus 1 persons arrive in T, and 1 person arrives in H. And there's just one possibility left, that k persons arrive in T. The probability times the probability that 0 persons arrive in H. Now here we have already this formula here. Now we can plug in. This equals to pk minus 1 t, and p, that the probability that one person arrives in time interval h is lambda times h. And for p0 we also know an expression. It is 1 minus lambda times h. So very well. This we can rearrange such that we end up with the following expression. So P K T plus H minus PK of T. Sorry for my writing. Equals pk minus 1 of t times lambda h minus pk t times lambda h. So this equation comes from this last equation down here. So comes from this guy here, yeah. This is just a rearrangement. Okay, and here we can divide by h. So this leads us to, sorry, pk t plus h minus pk of t divided by h equals pk minus 1 of t times lambda minus pk of t times lambda. And this part here on the right side does not depend on h. So here we can write the limit such that h goes to 0, and this is just then the differential, and we end up in dpk t times dt equals pk minus 1 of t times lambda minus pk of t times lambda. And this is now a mixture of a differential equation with a difference equation, because here with respect to t, this is denotes that it is a differential equation, but we also have the k's here, k minus 1, and this is typically for a difference equation. Now from literature, or let's say looking it up online on Wikipedia, usually you could make ansatz functions, let's say for difference equations, like, okay, you have fn plus fn minus 1 plus fn minus 2, something like this. You choose an ansatz that fn equals lambda n, lambda to the power of n, and for let's say a differential equation, let's say you usually use an ansatz and y is a function of t, e to the power of alpha t. And therefore let's make a guess for this mixture of differential and difference equations. Let's say that p, just write p, is a function of time equals some constant c times e to the power of alpha t, and alpha is some unknown parameter and c is an unknown constant. And multiply this with chi to the power of n, like we do it, or people do it usually for difference equations. And to specify this here, we also have a dependence on n, and to write it more strictly, let's c also depend on n, e to the power of alpha t, and chi is also a function of t to the power of n. And this is a sort of an educated guess, because it's well known that differential equations you solve this way, like this here. It's typically for solving differential equations of this type, with one time derivative, and the others are just function in time and no derivatives. And here the sort of a difference equation, usually you make an ansatz f of n is equals to lambda to the power of n, where, yeah. So if we plug this in, let's just write it again. So this is our equation which we try to solve. Times lambda minus p k of t times lambda. And if we plug in that our ansatz equals the pk equals c of, sorry, I forgot here the time dependence. That pk of t equals some constant, or not constant, multiplier that depends on k, times e power of alpha t times some unknown function chi of t to the power of n. So if we plug this in, we can use the product rule here. Let's differentiate this with the product rule. So what we get is, here of course it's ck. Then let's first differentiate this guy here and keep this constant. So we have chi, and I note here with this prime that it's the time derivative of chi. T, then we have to write n and key times key of t to the power of, sorry, this should be k, and this is also here k. Sorry, I messed it up here, because in my notes I've written it down a bit differently. Sorry about this. Hope I can make it. So here it is, k to the power of minus 1. Chi to the power of k minus 1. And with the product rule we end up with here, we also have to write k, then it's alpha e to the power of alpha t, and this chi function here remains unchanged. So let's check it. Oh, sorry. Here I forgot something. E to the power of alpha t. And this is then equal to, we have to just plug in. So here it's ck minus 1 times e to the power of alpha t chi t k minus 1 times lambda minus, and here we just have to put ck e to the power of alpha t chi t over k. Okay, and then remember in the past, so in the derivation we also had an equation that describes the probability of events happening during age. So we have this guy here. However, I messed it a bit up. Okay, now we have arrived at this equation, and look at this. Sorry, I'm a bit confused. Look at this differential equation here. If we derive this for k equals 0, then we end up with the following expression. So dp 0 over dt of t equals minus lambda p 0 of t times lambda. And if we plug in this ansatz here, we find out that alpha equals minus lambda. And if we put if we substitute here minus lambda here for alpha, then we see that this term here equals this term here, and therefore they cancel. Also, we can divide by e to the power of alpha t, e to the power of alpha t, and also we can divide by chi to the power of k minus 1 here, And what is left then is, it is ck chi prime of t times k equals ck minus 1 times lambda. So let me check if this is correct. K ck chi prime of t is equal to c of k minus 1 times lambda. And this is now also a differential equation. Let's arrange this. So k prime of t equals ck minus 1 over ck times k times lambda. And therefore, if we integrate, we get chi of t equals ck minus 1 over ck times k times lambda t plus d, some constant. And we know, please have a look at the ansatz function. Let's plug in here 0. So the probability that at 0 time a person arrives or an event occurs is 0. And we do not want trivial solutions, therefore the c case we don't want to be 0. Then e to the power of alpha t can also not be 0, therefore chi of t must be 0. And let's write this out. So strictly speaking, this means because chi of 0 equals 0, it follows that d equals 0. So let's write our expression for chi again. Chi of t equals ck minus 1 over ck times lambda t. And we assume that chi does not depend on k. Therefore, ck minus 1 over ck times k is constant. And just choose some constant and let's look what ck and ck minus 1 will be. So set this to 1. So ck minus 1 over ck times k equals 1, and just keep the k here, and here we can write, let's say this would be k factorial, and here, oh sorry, here it would be k minus 1 factorial, and here k factorial, and therefore it follows that ck equals 1 over k factorial. Now let's go back to the ansatz function we've chosen. This was pk over t equals ck times e to the power of alpha t times chi of t to the power of k. And basically we have now found everything here. Let's plug it in. So pk of t equals our ck we have found. It's 1 over k factorial. Then alpha we have identified as minus lambda. And we have set here this expression here, c of k minus 1 divided by c k times k. We've set it to 1. And then here it remains that chi of t is lambda t. And this lambda t we have to put to the power of k. And actually I think now we have arrived in an expression for the probability that k persons arrive at time interval t, which is an expression for the Poisson process.